Word up. Nationwide hated. Nickel plate.
Sequel or death? Yo, son, what are you going to choose? Yo, check it. This seminar is filmed at Carnegie Mellon University. Thanks a lot, Google.
Let's get started. We're excited today to have Yash and Gonzalo, both engineers at Startree, to talk about the query optimizer they've been working on as part of Apache Pinot. We have to give a special thanks for both Yash and Gonzalo for being here. Gonzalo is in Madrid in Spain, so it's currently 6 hours ahead of me, so it's 10:30 p.m. where he is. But Yash is down in India, where it's currently 3 a.m. It's not the record for us. 4 a.m. is the earliest, but still, it's super early. So we appreciate Yash getting up or staying up for talk to us about databases. So as always, if you have questions for the speakers as they're giving a talk, feel free to unmute yourself and ask a question at any time. And that way they're engaged in a conversation and not talking to themselves in the middle of the night on Zoom for an hour. Yash and Gonzalo, thank you so much for being here. The floor is yours.
Thanks, Andy. Thanks for having us. So, hello, good evening. Welcome to today's session in the Sequel or Death seminar series, where my colleague Gonzalo and I will be talking about Apache Pinot's query optimizer and the various optimization techniques that we apply under the hood of Pinot's distributed query engine in order to make it super fast. Just a sneak peek, we like SQL over here. We have no intentions of killing it off, but we do believe that certain use cases could be better served by specific kinds of query languages, and we'll touch upon that briefly in our talk later on. So my name is Yash, and currently working as a software engineer at Startree for a little under a year now. I work mostly on Pinot's query engine, and I'm also a committer on the open source Apache Pinot project. And prior to this, I was working on the Kafka Connect ecosystem at Confluent. I'm also a committer on the open source Apache Kafka project. And as you probably guessed, I'm quite passionate about contributing to these large open source projects, being part of these open source communities, particularly in the domains of distributed systems and data infrastructure. I'll just let my colleague Gonzalo go ahead and introduce himself now.
Cool. My name is Gonzalo. I'm working here from Madrid. I'm working on Startree for almost 3 years now. And I've been mainly focused on working on Apache Pinot. I'm a PMC member of Apache Pinot, and I've been working on distributed databases, on model-to-model transformation, which is a funny name to say that, transforming languages to other languages for almost 15 years. And yeah, I'm super happy to be here sharing all these cool tricks we are doing with you. So yes.
Awesome. So with that out of the way, let's take a look at the agenda that we have for you all today. We'll be covering a brief intro to Apache Pinot, focusing on the query engine aspects so that, we set a foundation for us to be able to talk about the more interesting stuff and optimizations that we apply, primarily in the area of joins and semi-joins, after which we'll talk about some more advanced optimizations, including stuff like dynamic filters and spools that aren't very common techniques across databases, before finally closing off with a bit of a recap, as well as a brief look into the future of Pinot. So yeah, without further ado, let's get started. Let's dive into the introduction to Pinot. Firstly, what is Pinot? Sure, it's a database, right? But there's a million databases out there today. Where exactly does Pinot sit in this vast landscape of database options that are available today? We call Pinot a real-time distributed OLAP database. It's a relatively new category, but a fast-growing segment. And this is defined by ultra-low latency analytics, so think millisecond latencies at extremely high query throughput. So again, think tens of thousands of queries per second on petabytes of data. At the heart of all this is Pinot's columnar data store, which has several smart indexing and pre-aggregation techniques. Another interesting characteristic of Pinot is that it scales really well. So you can simply add servers to your Pinot cluster, scale it out horizontally, both throughput and capacity, and Pinot will employ some smart techniques to make sure that the tail latency for queries doesn't get out of hand, even as your cluster size increases. So the primary use case for Pinot has been user-facing real-time analytics, which is quite different from traditional analytics that you've probably heard about internally in organizations powering business use cases. So In this user-facing real-time analytics world, we put analytics into the hand of end users through applications, which is also why we need to scale to these crazy numbers of tens of thousands of queries per second, so that use cases on Pinot can scale linearly with growth in users of your applications. Pinot can also be used for other analytical use cases, though, including internal dashboards, anomaly detection, ad hoc data exploration, and various other use cases. So why Pinot? To convince you all that all the optimizations here that we're going to be talking about in the rest of this talk are not just theoretical or aren't just something from some esoteric database that nobody uses or cares about. Let's take a look at some of these numbers, right? Some of the biggest companies are using Pinot at massive scale to power various use cases that most of us probably interact with on a day-to-day basis. So LinkedIn is where Pinot was originally created. They're serving a massive 650,000 plus queries per second today from their Pinot clusters, powering 100 plus products, including things like who's viewed my profile, post analytics, hiring analytics, and various other use cases. Uber is also using Pinot at massive scale for a very diverse set of use cases, including system log analytics using the compressed log processor framework. They're using it for the Uber Eats restaurant manager app, putting analytics right into the hands of restaurant and business owners to keep track of the health of their delivery business. And Stripe is also using Pinot for a bunch of interesting use cases. You can see the numbers here, they speak for themselves. Pinot is used in production at massive scale all over the world. All right, now that you're all hopefully convinced that Pinot is a database widely used in the real world, let's take a look at how Pinot stores and queries the data. So like most other databases, Pinot stores tables, and these tables are divided into disjunct segments that are the atomic storage unit in Pinot. These segments are formed by columns. Again, remember, Pinot is a columnar data store, and these columns themselves are formed by various indexes, so various single column indexes. We have a dozen indexes, something for every use case. So we have an inverted index, a range index, we have geospatial indexes, we have JSON indexes, we have text indexes for text-based search, and various others. And talking about the compute part of the equation, Pinot has controllers, brokers, servers, which are all distinct kinds of nodes in the cluster. Controllers are sort of the brain of the cluster, managing metadata and cluster coordination, but they aren't very involved in the query execution part in the query engine itself, so we won't be talking too much about the controller. Servers are the ones that are actually storing segments on disk locally and also doing the bulk of the query processing work. So these segments are actually stored typically in more than one server through replication for both high availability as well as for scaling throughput. And brokers are the ones that actually receive SQL queries from clients. They compute an optimal query plan from the SQL queries received from the client and dispatches them to the servers. So it typically, as part of computing the most optimal query plan, also includes the set of servers that the query needs to be dispatched to, as well as the set of segments that each server needs to process for that query. So the single stage query engine. This is Pinot's original query engine, the first query engine that supports projections, transformations, aggregations, group bys, UDFs, a bunch of other stuff. But it does not support more advanced SQL constructs like joins, subqueries, window functions, and a bunch of other things. And the reason for that is that it uses a simple scatter gather execution model for the queries, wherein the broker receives a query, scatters request out to the servers that it computes as part of its query plan. The servers do the actual processing of the request by running a bunch of compute on the segments assigned to it, returns the response back to the broker, which gathers all these responses from the servers that it scattered the request to, before sending back a final response to the client. So as you all might be familiar, the bottleneck in a lot of databases is typically I/O. So a lot of our optimizations are focused on reducing the amount of I/O done to serve each query. In the single stage query engine, one form of doing so is using various pruners on brokers and servers. So for instance, on the broker side, you'll use pruners to reduce the number of servers that you need to fan out a query to, using metadata like partitioning info, using other metadata like time boundaries and stuff like that. So that's going to reduce the number of servers that the broker scatters the request to. And on the server side, we again use more pruners to reduce the number of segments being processed, to reduce the amount of I/O done, to reduce the amount of compute done via more segment level metadata like column value information, column statistics, Bloom filters, and other techniques. So one thing I forgot to mention earlier is that tables in Pinot can be partitioned on columns, so physically partitioned. And this will be important to remember later on. So just keep that in mind. So we can have partitioning in Pinot tables. Coming to the most interesting optimization that we actually apply in the single stage query engine, that's going to be indexes. These can massively reduce the amount of disk read needed to, serve a query. So again, these are going to be indexes like inverted indexes, range indexes. All of these are single column indexes. The most interesting one is actually the star tree index, which is Apache Pinot's USP. And in fact, so this index actually does a bunch of pre-aggregations that can speed up aggregation and group by queries by orders of magnitude. It's a super interesting topic and it can have an entire talk dedicated to it. And in fact, does have an entire talk dedicated to it in CMUDB's 2021 seminar series. So I'd highly encourage you to go check that out if you're interested in it.
A quick question. You said star tree index
Yep.
is it's the system is USB, or what phrase did you use?
USP. Like
USB.
it's
Okay.
yeah, one of the most popular features of Pinot, USP.
Got it.
Yeah.
Okay, awesome. Thank you.
Cool. I think there was another question on chat.
Yeah, the indexes are indeed segment level. That's right.
Yeah. Yeah. So Yash has been talking about the single stage query engine, and as he mentioned, one of the limitations we have there is that we don't support some very interesting SQL features, like especially joins, window functions. We also don't support in single stage. We don't support unions, things like that. That's why a year and a half ago, more or less, we introduced the multi-stage query engine. We released that in Apache Pinot 1.0, and this multi-stage query engine is an iteration on top of the other one. The idea here is that we, instead of having an expression tree and evaluating that in a scatter and fungather fashion, the thing we do is to create several stages, which is one is actually a scatter and gather phase, and then the query is divided in these stages, and then these stages are, we assign a parallelism to each stage, usually in the way that we create virtual partitions on the data that we are going to analyze. So we, from the normal operators we have, we go to stages, and from stages we go to what we call workers. Workers are different instances of the stage that are going to see a partition of the data. And by doing that, we are able to execute things like joins in a distributed way without having to use all the resources in a single machine. And that's a key feature in this multi-stage query engine. So important that we actually name the engine that way, right? In this model, the broker still does a lot of work. Here, when we receive a query in the broker, the first thing we do is to optimize that, applying some normal SQL tricks in the relational algebra. And then the most important part, at least in the context of this conversation, is to decide how to split these operators, or how to group these operators into stages, and how to assign workers to these stages, and also how the information is going to be shuffled between different workers. Okay, that's the most important part. Usually, when we have to, in general, when we are distributing that information, we use some exchanges, which is a logical entity in this diagram here. It doesn't mean that we are going to move all the data to some place and then distribute that. That's a logical view, but in the implementation, the thing we actually do is to send information from server to server, on specifically to worker to worker. This information can be either sent to a different process, which is done using gRPC channels, or in case we are able to send that information from the same, inside the same process, two workers running in the same process, then we just share memory with in the same GVM, because Pinot is a GVM-based system, and that's super efficient and one of the things we try to do all the time, right? Apart from that, just slight parenthesis and probably more focus on what this seminar is about. For us, SQL is just a front end, an interface, right? We do not apply optimizations at SQL level. We always transform that into the relational algebra in some specific nodes we have. We are using Apache Calcite to do that, and we are reusing most of the things in Apache Calcite to skip some of the work and also apply some of the rules they already have. And the reason why we decided to use SQL is not because, we like SQL, but the actual reason why we choose SQL is because it's the lingua franca in the OLAP world, right? And when I say the lingua franca, in the same way we are now, all of us, we are talking and discussing things in English. Even if my English may not be the best in the world, you are able to understand me. And the same thing happens when you have different SQL dialects, right? We are not going to be able to run the same SQL that is being executed in Postgres or in other database. But a person writing a SQL expression in one of these databases is probably going to understand one of a different expression written in the SQL dialect we are using, right? So that's what is great from SQL. There are tons of problems, but the important part here is that for us, SQL is not something that we are bound to, and we could be using other languages. And in fact, we are right now. There are people in the Apache Pinot community working on the ability to support different languages. Especially, we are focused on time series, because we understand that in the same way that SQL is the lingua franca in the OLAP world, when people is used to use Grafana to monitorize some application, usually the thing they use is to write PromQL. So that's something that, for example, it will be super useful to support. When I say that, imagine this simple query where we are reading from a memory use table, and there we are applying some filters and grouping by the pod name, and then producing some outputs and some number gates, right? The thing we actually have is something like the one we have in the right. This is super simple, but the idea is that we have we are scanning the table, then applying a filter, and then applying an aggregate. This is the logical view. Then this is what usually the broker produce, and then this is optimized on each server based on the segments we have and these indexes we have on each segment, because they may change in time, right? So this, for example, maybe this filter where we are applying an AND and blah, 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 it can be optimized, for example, to say, okay, I'm not going to use just a filter that applies this AND, but I am going to use a filter that actually reads using this specific index or whatever. Super classical in the database world, nothing super new. The point is, the same model could be generated by some LINQ query. We don't support that in Pinot, but it shouldn't be super difficult to add that. It's a matter of creating the grammar. Once you have that, generate the nodes you have at the right side, right? We could be using N3QL, which is a language created by Uber and created specifically designed for time series. Or we could be using PromQL, and in the future we would like to have something like that. And I hope this is not gonna be. I hope it's gonna be soon, right? Or it could be same IR, right? It's the same thing. You could be generating anything to that intermediate model, and then you can move from there to our own Pinot specific model, right? Sometimes there are gonna be some operators that are just specific for your language. Probably they could be also represented in the relational algebra, but sometimes it's going to be easier to just move to some specific node. And we know that, for example, for some operations in the time series, we may want to add some extra nodes apart from our own joins and stuff. But in general, they are going to be pretty similar. Okay.
Right, so just so I understand, yeah. So like this, say whatever query shows up, it gets parsed, and then the broker generates, which is roughly a logical plan here.
Yes.
And then you ship that logical plan to every single server, who then runs their own optimized to convert the logical plan into a physical plan.
Yeah. In fact, the servers, the thing they run, well, depending on the stage, it's a leaf stage in our tree or the classified graph we build on top of the workers. But in the leaf stages, we run the same SQL engine, the same single stage query engine. So there we apply all these physical optimizations based on the indexes we have. The main reason is because sometimes for historical reason, but also because we are storing so much data with, in case you want to use the same table you were using and then you add a new index, you don't want to re-index everything, right? So there are going to be some segments that are going to be using newer indexes and some segments that are not going to be using them. So we are not able to store all the information of which indexes, which segments contain which indexes in the broker, because there may be tons of segments and we don't want to spend that memory there. So it's given that the optimizations we are going to do, they are not super based on the indexes. We can just evaluate that latest optimization to transform these logical nodes into physical nodes. It can be done pretty fast in the leaf stages, and we do that for every segment, and we do that in parallel and whatever, but it's super fast because we apply eager optimizations, and we are not doing some kind of like cost-based optimization at that point because it's not super interesting. Because if you can use you can use an inverted index, that's going to be the fastest. And if you can use if you don't have that, but you can use a range index, maybe that's going to be better, right?
Okay, here's my question. It's like it's so it sounds like you're basically just doing a greedy search, a brief force search to say, here's the best index I have and my choices available to me. Just pick that and not try to do anything fancy. And then, and then I think you said the multi-stage thing you released in Pinot 1 that is doing joins, correct?
Yes.
And then so is the broker deciding the join order up above?
Yeah, we are going to talk about that.
Okay.
But the spoilers, the thing here is that we want to add some cost-based optimization in the brokers, just mainly to decide things like that. Right now, we don't have that, so we are using a very fixed order where, for example, we always use apply hash indexes, and hash indexes, the right-hand side is the one that is always being hashed. It's not super smart, but it's a good compromise right now. And in future, we would like to use some statistics, but there is some discussion to have there. So yeah, yes, I'm giving you the spotlight.
All right. So it's time to get into the meat of this session, and we're going to start talking about join algorithms and join strategies. So these are two distinct things, and join algorithms are referring to the actual algorithms that are executed on data that's already in one place to emit our join output. And this is stuff you've all read about in classical database literature. So there's going to be stuff like hash join algorithms, sort merge algorithms, and nested loop join algorithms. So in Pinot, we primarily use hash join algorithms. So where there's a build side, there's a probe side. You build up a hash table on the build side using the join keys as the lookup key into the hash table. The probe
Ash, are you
side
sharing your
is
screen?
I am.
Okay.
Is it not visible?
It looks correct to me.
Okay, cool. Thank you for it.
All right. So the probe side is implemented as streaming input in Pinot, where you have rows coming in one by one. For each row, you do a lookup on the build side. You see if there are matches, create the join output, and keep doing that. And depending on the kind of SQL join it is, we might also need to keep track of unmatched rows. So for instance, outer joins, left join, right joins, full joins, stuff like that. And this is typically used for equi-joins. For non-equi joins, we do have to fall back to the nested loop algorithm, where we iterate over all the rows for one side. For each of those rows, you iterate over all the rows from the other side. Super inefficient, quadratic time complexity, horrible. We don't usually want to do that, but that's also an option in terms of the join algorithms. But that's actually not the interesting part. The interesting part is the join strategies, which is what we're referring to for the various strategies we use to actually get all the data into the right place in order to execute the join. So for a distributed join, the challenge is to get all the data to the right place and make sure that we are respecting the join semantics. For classical databases like Postgres and most other single node databases, This isn't really a problem because all the data is already on a single node. Even if there are multiple servers, each server is going to have an entire copy of the data, right? The servers are just going to be there for, say, high availability. Whereas in a distributed database like Pinot, where the data from tables is inherently spread out across multiple servers, we need to make sure that all the data that needs to be joined is in the right place. And this is going to involve data shuffle over the network across servers. And this is expensive IO. This is typically going to be a bottleneck for join queries. And it is going to be our goal to optimize this data shuffle, this network IO overhead, and minimize it as much as possible. And that's what we're going to talk about through all these join strategies. So the most simple way, the absolute most simple way, the most straightforward way to execute a distributed join would be to move all the data from both sides of the join into a single server, execute a join algorithm locally on all that data, and emit the final result, right? So in this case, you have 3 servers and a couple of tables A and B that need to be joined with segments spread out across these servers. And in this case, suppose we want to move all the data into server 2. That would involve some data shuffle for segments that are on other servers. It would involve some in-memory movement of data that's already on that server. Similarly, for segments of table B, some data shuffle over the network, some in-memory data movement. But once we have all the data on a single server, we can execute our join algorithm locally on that server and emit the final join result to the broker before sending it back to the client. The number of rows shuffled here would be bounded by the total number of rows across all segments of both sides of the join. While this works, it is not scalable. So remember, Pinot can have dozens of servers, hundreds of servers, and petabytes of data. And joining 2 large tables by sending all this data over to a single server and executing this massive join is just not going to work very well. So we don't actually use this strategy in Pinot. This is just to illustrate the problem of data shuffling in join, where we need to get all the data into the right place before we can make our join executions happen. So instead, what we actually do is we create virtual partitions at query time, and we'll see what that looks like through a bunch of strategies. So the first one is the query time partitioning strategy, which can be used for equijoins. So join conditions like a dot some column equal to b dot some other column. So in this case, we can do something called partitioning. Again, at query time, we're going to use a partition function that guarantees that if a dot some column is equal to b dot some column, the join condition, if that condition is true, then the partition value emitted by the partition function, which is typically going to be a hash function, is going to be the same. So let's take a look at this example to see what I'm talking about, right? We have, again, similar setup, 3 servers, 2 tables that need to be joined, few segments scattered across these servers for both sides of the join. We're going to create virtual partitions. So let's say P0, P1, P2, and these partitions are going to be the same for both sides of the join. And these partitions are going to be in the same server. So P0 in server 1, P1 in server 2, P2 in server 3. And now what we're going to do is for each row in each segment, we're going to compute the virtual partition and send the data over to that virtual partition. So for instance, for every row in every segment that computes to partition 0, we're going to send it over to server 1 in the virtual partition P0. And that's going to involve some data shuffle over the network. It's again going to involve some in-memory transfer depending on where the actual data is, the physical data is. Similarly, we're going to move over data for the other 2 partitions. And now we can simply execute our local joins on each of these servers. And because of the property of the partition function that we choose, we can guarantee that rows that end up in different partitions didn't need to be joined in the first place. So we are maintaining the join semantics while also being able to distribute the join across multiple servers. So once we have these 3 local joins that are executed, we can simply combine the results, get the final join output, and send it to the client. So again, the number of rows shuffled here is bounded by the total number of rows across both sides of the join. And the worst case would be when each row in each segment needs to be shuffled over the network to be sent to a virtual partition on another server. That strategy, while good, doesn't always work. So think about non-equijoin conditions, right? Like A dot some column greater than B dot some column, or A dot column not equal to B dot some column. In this case, we can't partition both sides of the join because some rows would never be joined in that case. Let's just take the same example to see why. So here we have, again, similar setup. And here we are going to create partitions for A, but the other side of the join is actually going to be broadcast to all servers. And if we don't do that, if we were going to partition both sides similar to what we did earlier, what's going to happen is that the rows that are sent to one partition are never going to be joined or matched with the rows that are sent to another partition. And the join condition is such that that's going to break the join semantics, and we can't do that. So what we do instead is distribute one side of the join, partition it. It doesn't really matter what the partitioning strategy here is here in this case. It could be random, it could again be hash based, doesn't matter. So we're going to partition A, and similarly send rows that compute to partition 0 over to partition 0 and server 1. And similarly for partition 1 and 2, some data shuffle is going to be involved, some in-memory data movement is going to be involved. And for table B, the other side of the join, we're going to broadcast the rows to all the partitions. And this is going to ensure that the join semantics are retained. And this strategy is typically good when one side of the join is much smaller than the other side of the join. And we can ensure that we broadcast the smaller side of the join, and the larger side is the one that's going to be partitioned. So the number of rows shuffled here in this case is going to be bounded by the number of rows in the partition side plus the number of rows in the broadcast side multiplied by the number of servers that we want to execute the join in. So note that we can also control the number of servers that are actually executing the join, or the join parallelism. And again, that's going to have a few trade-offs. We could execute our joins in more servers. That's going to involve probably more data shuffle, but we're also increasing the parallelism of our join compute. So that's another trade-off that needs to be considered.
Can you share
And
how are you collecting the statistics to decide whether which of these approaches to do? Is it because on ingest you're maintaining the stats, or you're running analyze? Like, how does that work?
we'll cover that briefly after we talk about each of these strategies. But
Okay.
spoiler is
Fine.
that we currently don't do too much smart stuff there, and we rely on various heuristics and user provided hints to choose the best strategy based on the data layout and the query pattern. But yeah, we'll cover that a bit more. Yeah, so a variation of the previous strategy is the broadcast plus local join strategy. So again, this is similar to the previous strategy, can be used for non-equi joins and various other cases. But here we are going to broadcast one side. The other side is not going to be distributed at all. So the broadcast side is going to shuffle over all the data to the servers that already contain the data for the other side of the join. Again, this is going to be super efficient for joins involving tables of skewed sizes. So one super large table, one super small table, and we're going to shuffle over the data from the small table to all the servers that already contain data from the larger table. In this case, so let's say A is the large table, that's going to be the local side of the join, and B is the small table, that's going to be the broadcast side of the join. We're simply going to move over the data from B to all the servers that have the segments for A, execute our local join algorithms on each of these servers, and combine them to get the final join output, right? So the advantage here is obvious. One side does not need to be shuffled. This can be great, again, for when tables are skewed in size. The disadvantage compared to the previous strategy is that it can't scale to more servers than the ones that are actually hosting the data from the local side of the join. And this is usually not going to be an issue, but it could be an issue in certain edge cases. So think certain joins like cross joins or Cartesian products where the join is actually going to create an explosion amount of data, and we might want to spread that load out across multiple servers. But usually this strategy turns out to be more efficient. And the number of rows shuffled here is simply the number of rows in the broadcast side multiplied by the number of servers that are actually executing the join. So moving on, we have something called a co-located join that completely eliminates data shuffle. So this requires a number of conditions to hold. So this is going to be useful only for equijoins. So again, two columns being equal as the join condition. And the two tables need to be physically partitioned on the join columns, and the partitions need to be co-located. So what that means is that the partition function used for partitioning each side of the join, each table in the join needs to be the same. The number of partitions needs to be the same. So the assignment of partitions to servers needs to be the same, and we need to have servers that hold all segments for each partition of each of the tables in the join. So that's a whole laundry list of conditions, right? But when all these stars align, we can actually execute a co-located join, which completely eliminates data shuffle. And this is going to speed up queries by like an order of magnitude or two. So it's usually worth it to architect your data layout to match your query patterns to, be useful for the common join cases. And Pinot does support a bunch of table configurations to make sure that the partitioning is, going to support this sort of strategy. So again, taking a sort of similar example, 3 servers, 2 tables that need to be joined. Both these tables are partitioned on a certain column that is going to be the join column in this query. And we have, let's say, 2 partitions, 0 and 1. We have server 3 that's hosting all the segments of partition 0, server 2 hosting all segments of partition 1, again, across both sides of the join. So here we already have our partitions available, right, on the same server. So our virtual partitions are simply going to correspond 1:1 to the physical partitions, where we have P0 on server 3, P1 on server 2. And since we already have the data partition, we can simply execute local joins by doing in-memory data movements without any network overhead, no data shuffle required. Simple local joins here, combine the join results, get the final join output, and return it to the client. So again, since we are eliminating all the data shuffle overhead, these joins are much, much faster options than the other strategies. And interestingly, many other distributed real-time OLAP databases only support this strategy, whereas in Pinot, it's just one of the many options, but of course, the most efficient. And we'd always try to aim for this sort of join strategy whenever possible.
Wait, so these are the gamma join algorithms from the 1990s, as far as I understand. Like, is there anything novel specific about the Pinot, like the environment you're working in, where like you can't take the classical join algorithms or distributed join algorithms and make this work, or is it just it's almost a textbook implementation? And it's okay if it is. I'm just curious.
So yeah, in terms of broadcast and shuffle and the logic involved there, it is pretty much all the same. We do have a lot of low-level optimizations, but from a high level, the actual strategies to, get all the data into the right place, I think, yeah, that's the pretty classic strategies that we are using.
Okay, thanks.
So we have a variation of the co-located join strategy as well, called lookup join, which is very Pinot specific. So we have these dimension tables that are sort of replicated across all servers and materialized in memory in each server as a lookup table. So these are typically for like small tables that contain dimensional data, like product information, customer information, time ranges. And we can execute joins with no data shuffle, even in this case, using these in-memory lookup tables for one side of the join. And yeah, moving on, we want to talk a bit about how rules are applied. We briefly touched upon that earlier, but Pinot does not use cost-based optimization, at least not yet. Instead, we eagerly apply optimization rules. So Gonzalo briefly mentioned this earlier, but we also do a bunch of stuff, obvious stuff like, pushing down filters into joins, pushing down aggregates into joins. We have some rules that can convert joins into semi-joins whenever possible, and a bunch of other stuff. We also need to choose strategies for join, the data shuffle, and stuff like that. So right now, since we only eagerly apply these optimization rules based on simple heuristics, some rules can only selectively be applied with user-provided hints. So right now, that's not optimal. We rely on users to know their data layout and their query pattern, and sort of choose the best strategy for their data layout. And that's going to be a bit of trial and error. But the reason for this is that brokers currently have very limited knowledge of the table statistics and also the disk level layout for segments. And it's going to be prohibitively expensive for brokers to maintain metadata for millions of segments potentially all centralized and make decisions on that. So we do want to support smarter optimizations. In fact, we have been discussing about potentially supporting either cost-based optimizations or history-based optimizations where we could optimize queries based on historical query stats for similar queries. But one thing we need to be super careful about is the optimization overhead. So right now, our optimization process is super simple, right? We just apply these rules eagerly and compute a query plan that may not be globally optimal, but is definitely more optimal than the obvious thing. So we need to be very careful that the latency overhead introduced by this sort of optimization is actually worth it, because Pinot, remember, is typically used in a lot of low latency environments and low latency use cases. So we need to be sure that the overhead introduced from the optimization isn't so high that the optimization itself, doesn't become worth it anymore.
Yeah.
Go ahead.
No, go ahead, Andy.
All right, so when a query shows up on the broker, that runs calcite to do the conversion to the logical plan. And then when it lands on the server and you convert it to the physical plan, is that calcite again, or is that all Pinot code?
That's not calcite. So calcite is purely at the broker level at this point. We compute, so we use calcite to parse the SQL as well. We get the abstract syntax tree. We use a calcite query planner to convert the abstract syntax tree of SQL nodes to relational nodes and relational logic. And then we use a bunch of rules, both from calcite and Pinot custom rules, to actually convert these trees of relational nodes into semantically equivalent but more optimized forms. And once we send over these logical plans over to the servers, it's all Pinot optimizations from there on.
And then on the server, like, is it a bunch of Java code that you're firing off in a specific order to apply the rewrite rules, or is there like a DSL or something you're compiling into Java? Like, how are you defining those rules that happen on the server side?
No, it's just plain old Java applying some specific order. In fact, we had to do some tricks to support different alternatives and stuff because it's pretty much static right now. Another thing I wanted to say is that even we have some rules that has to be enabled by using some hints and stuff. Some of the distributions we Yash was talking about before can be automatically inferred by the broker. For example, collocated joins can be inferred by the broker because it knows how segments are distributed between servers. Segments are distributed between servers. So it's able to decide automatically whether it has to use this technique or the other. There are some cases where, for example, he was saying if we have a very, very small table in one side and maybe we just want to broadcast that side to all the places where we already have the larger one, that's the kind of things we cannot do because we don't know, the broker doesn't know how large are the tables. So that's one of the things we want to introduce in the future, probably this year. But again, it's something we need to do carefully and without actually modifying too much our making our optimization process too slow, right? So
quick question I had, when you're doing these joins with these different strategies, what happens if in a single server you don't have enough memory because you may not have the perfect partitioning function, or when you're broadcasting, you may have, do you do something else to react to that?
In that case, we have two options. You can either make your query fail or you can return partial data. Right now, we don't have the ability to spill out to disk or something like that. That's something we could be thinking about, but our use cases are not queries that run for 10 seconds or 60 seconds to produce a result. Our use cases run queries that finish in less than 1 second. So if we end up having to go to disk, probably we are going to be out of the actual timestamp we have.
Got it.
Right?
I think so
that's not. I mean, in case you want to do that kind of things, you can, for example, use Trin on top of Pinot, and it's something that our customers have been doing for a while. The point here is, okay, you want to have super fast queries for your panels or stuff. Right?
That makes sense. And sounds like in your workload, you're not going to have like 10 joins or 20 joins. Sounds like you're going to have
absolutely.
Right? So that's what you're optimizing all these things for, and you really want to go fast. Okay, got it. Thank you.
Let me sure.
Okay, over to you, Gonzalo.
Yeah, let me sure I'm sharing. Cool. Here we're calling this advanced optimization, but probably it's not advanced. But given the previous optimization were focused on reducing data shuffle, Here we are focusing again on trying to optimize also disk usage, right? The first optimization I'm going to talk about is the pipeline breaker. We call that to some specific optimizations for semi-joins. Consider, for example, this query where we have a very large table that is joined with another, well, in this case, it's a semi-join with a subquery, which in fact is just reading from another table. Let's assume that table 2 is super small. In a normal case, this will need, we will need to scan the whole large table and the whole small table, and then apply for each row, load that in memory, right, and then apply the filter for each row. That's not super efficient, and the thing we do is to execute this small algorithm, right, where we are breaking our optimize plus execute pipeline into different stages, different parts, not the stages in the sense that we were talking before. The thing we do is to first evaluate this one in purple, the subquery. Once we have that value, then we can say, okay, cool, this is not super large. So the thing we are going to do is to substitute this value, and instead of using the scan, the thing we're going to use here is the actual result in a, let's say, literal way. It's not actually literals we are writing in SQL. It's different. It's implemented in a different way, so we don't actually have to have these huge SQL sentences. But if these values are in the order of hundreds or maybe few thousands, we can execute this kind of query where we are actually, the thing we are going to be executing later is just filter, a normal filter, like if the user was actually been executing the first query, then going back to the application and then create a new query using the value in the in clause, right? So by doing that, we can compile this when the query reaches the servers can optimize that and say, hey, cool, but I have an index on large table.call2, so an inverted index, for example. So I can use that to evaluate this filter, right? So by doing that, we don't need to load all these rows, but only the ones that are actually going to be used, right? This is a super cool technique. The improvements in performance are massive what you can use that. And we are also able to use that in other cases, not just semi-joins, because as you may know, some inner joins can also be transformed or are semantically equivalent to a semi-join, right? In this, for example, in this case, it's pretty similar to the one before, but in this case, instead of using a semi-join in the select in syntax or where in syntax, we are using semantically the same thing, but using an inner join, right? Which is, again, equivalent to this thing. The point is that not all joins can be transformed into that. For example, it can only be used in inner joins. One of the sides has to not be used in the projection phase. And also, which is very important in our case, that side of the join has to be unique by these keys. That's super important. And it's something people usually forget about. In a standard database like Postgres or MySQL or whatever, you have some indexes saying, okay, this is a primary key, so it's unique. Don't worry too much. The database about that. You can apply that to the kind of optimization. But here we don't have that, because in the OLAP world, it doesn't usually make sense to have that unique component, right? So there is nothing in the schema saying that, and therefore the database doesn't know anything about that. So again, this is one of the places where usually Pinot needs help from the user, and you can specify, or you could use a hint to say, hey, assume that this site is going to be unique by the column we are using, or instead of that, you can do something like actually write a distinct sentence in that subquery, right? For example, in this case, the right query is far more efficient in Pinot than the left, the one we have in the left side, right? Even if we are doing, in theory, more things, because we have to actually calculate this distinct. But given, for example, Pinot usually use dictionaries, this distinct sentence is super fast to evaluate, right? And in this case, users have to write the right-hand expression because it's semantically in SQL is different than the one in the one on the left, and it's different because in the left expression, if there is a row that is repeated, a value of call 3 that is repeated, any value that matches that is going to be produced, generate a new value, a new row in the result, right? And this is something that is usually super complex to explain users because they assume or they know for the domain, because maybe this is not super simple query, but they know that by applying some extra where conditions, they know that in their domain, that column is going to be unique. But the engine doesn't know that, right? So that's something we need to help the engine with. And it's, again, one of the places where SQL gets a little bit tricky. And one of the things that probably could be improved at some next level language. But that's what we have right now. Now I want to talk a little bit about a different thing, which is spools, which means the ability we have to do not evaluate things several times in all our goal, and especially now that a lot of queries have been automatically generated either by ORMs or BI applications or even AI. It's important to know that in these queries, like the one we have in the right hand side, some relations, some with expression are used several times in the same query. We need to think that queries that we are executing usually are like 400 lines of code, right? And they are repeating a lot of structures. And therefore, we don't want to evaluate that code several times. And spools are a tool we have to try to run these expressions only once. For example, here, let's assume that this diagram here is equivalent to the one we have in the right side. Here we are materializing this tiny relation twice, right? One in the filter and one in the as part of the join, right? And the point here is that we could and we are able to evaluate that stage only once, and then send information to using the same exchanges we are using. Send that information to two different stages. Here we have a stage running this part, and here we have another stage running the join expression. And this is also a tool we can use to improve normal joins, even if applying this pipeline breaker technique without having all the requirements, right? And this is what we call dynamic filtering. This is a funny feature because the idea is to make your query faster, but making it more complex. The idea here is to support, again, the same pipeline breaker feature that is super useful to improve your queries, but being able to use that in cases where they are not just semi-joins, right? The idea here is that, let's imagine that we have this query here, right? This query here is a inner join, but in this inner join, we cannot apply the same technique we were talking before, because we are first, let's assume that obviously tiny table is the tiny one, and we would like to apply this semi-join technique into this tiny table. So we cannot do that because first we are projecting column 4 from B, and also we have this expression here, and again, the database doesn't know whether b.call3 is unique or not. So we cannot apply the semi-join optimization. But the thing we can do here is to rewrite this expression, and users could do that manually, but we don't want that. And they could uglify their query by saying, okay, cool, instead of having this thing, let's make it more complex. And this is pretty similar to the thing I was showing before with the spool, right? Let's make it more complex. Let's keep the join we had before, but add another filter. And in this filter, we are going to read again from tiny table, right? Then, spoilers. Then we can use that and the pipeline breaker feature to compile this right-hand side from the join, right? And compile that to actually use the index, for example, the inverted index that we can use in this condition, right? So that's the idea of dynamic filtering, right? This is a feature that is not supported yet in Pinot, but it's supported in the databases like Trino or Alibaba's Analytics DB for Postgres. And it's something that has been proven very useful in some cases. For example, TPCH, there are some queries that are optimized in, I don't know, 1 or maybe 2 orders of magnitude by using these techniques in Trino, for example, and also in Alibaba's. This is something we want to add into Pinot. I don't know exactly when, but it's something that we want to add, and we are going to be working on that. And the idea, the implementation here is talked to you about pipeline breakers and I talked to you about spools. The idea is to combine both, right? So we can combine both to have the same functionality provided by all these other databases. In fact, we expect that it's going to be even better because in Trino, for example, there are like more data that has to be moved and things like that. Things have to go to the broker and stuff. In our case, that's not going to be the case. So I think this is going to be a super interesting feature that we are eager to have.
Wait, so it's basically a style of like sideways information passing, but like you're computing something like a Bloom filter or whatever on the side, and then you're using that to filter the large table as you're going into the join.
Yes. So
Okay.
we don't need to, I mean, we can prune a lot of rows and we don't need to actually materialize them and then send it through the network, and right?
Yeah. Okay.
So just a closing notes, really fast. We already talked about that, but Pinot is a distributed real-time OLAP database. We choose to use SQL as language, and right now we are working on supporting other languages, but under the hood, they are going to be working in the same way. We are going to transform everything into this relational algebra and our model, the different models we have to support that. And then we are using our tests. We are actually able to use the same optimizations that we have been using in multi-stage query engine for other languages without having to deal with SQL, because again, SQL is just syntaxes, right? For us at least. And with that, I think that's most of it. Our software is open source. There you have a beautiful QR you can use to check for our beginner tasks if you want to contribute. Usually all these large features are the first design, and then we start with implementations, and you can discuss about that. For example, I think the slides where we were talking about the spools, the link is there. And with that, that's all. I would also like to share this latest slide with you, which is a raffle we are having for all members of this event. You can join then if you want, and we are raffling this super funny T-shirt with the logo of StarTree, which is super cute.
All right, awesome. I will clap on behalf of everyone. Thank you so much for the talk, Gonzalo and Yash. All right, we have time for a few more questions. If you have any questions for the StarTree guys, just unmute yourself and fire away. Go for it.
So a quick question, in your workload, what tends to be the bottleneck? Is it aggregation or joins? It seemed like a lot of your queries are likely lots of heavy filtering on the base tables, even though they might be big joins, and then tons of aggregation. So is the bottleneck often aggregation or joins, or it depends?
It depends a lot on the kind of query that has been written, right? With SQL, you can shoot yourself in the foot and you can do tons of incorrect things. So it's very easy, for example, to reach the max number of rows we have configured in both aggregations and aggregates and joins. But usually with well-formed queries, I mean, if you are just exploring the system, it's pretty easy to mess up and generate very large queries. And these queries are going to be kill and timeout and whatever. But usually when you are running that, let's say mature code, mature queries that has been running for a while and you know them and they are fine. Usually the bottleneck is actually IO in most of the cases, unless you are actually doing some heavy work especially in joins. Joins are usually problematic if you want to deal with a lot of data, right? So the good thing here is that you can scale horizontally if you need in most of the distribution models we are using. And usually that's the main issue. And also, as we were discussing before, the system is written in Java, so you don't want to allocate. Allocating Java is super cheap. The problem is that once you end up reaching your maximum amount of heap, you are going to start, the system is not going to blow up, but instead it's going to be slowly trying to collect memory, so your latencies are going to get worse, right? That's the most common case. But the good thing is that has usually good solutions, right? Try to improve your queries for scale.
One last quick question is, do you work in cloud storage like S3, or do you have to do, and if you do you do some special stuff in that setting? And I know we are running out of time, so maybe quick answer.
First of all, in this, I think you're going to be able to join our Slack community. We have an open source community and also one focus on Star3. Feel free to ask any question you may have after this, Doctor. But the answering your question, we have in open source Apache Pinot, we have some techniques to deal with use features like S3, for example. All the segments can be stored in deep store, so you can distribute them easily or spawn new system without having to share segments from one server to the other. They can be automatically downloaded from there. In Star3 in our proprietary software, we have some extensions, and one of them is the ability to actually store all the segments, or your segments in S3, and then just download them, download the columns as you need them in your queries. So that's obviously gonna hurt your latency, but not that much. And usually it's very useful when you have to store, for example, for legal reasons, you have to store information for several years, and you are not consuming that or querying that super often. It's good to have that feature there. In case you are not gonna you don't want to pay for all the disk in EBS, then you can use S3 to run your queries as well.
That's great. No, interesting talk, and definitely this workload is super interesting and not something that traditional OLAP systems cover. So that's very cool. Thank you.
All right, I have a last question real quick. Can you just talk about any problems or limitations you guys have faced with Calcite? And then did you guys end up hard forking it and sort of maintaining your own branch, or are you just following along what are the mainline releases?
We have some discussion about that in the community because there are people that love Calcite, there are people that hate it. Calcite is super complex, it's super complex, and is touching so many different places and introducing something that from one version on the other something breaks, and it's sometimes it's a pain, but at the same time it provides tons of functionalities. We are not forking Calcite. The thing we forking somehow is like we actually have our own code for the parser, using the same parser they are using, but adding some features by ourselves. But we are not forking the code. There are some discussions in the community between different committers whether we should be using our own SQL or relational logic model with their own optimizations and stuff. Depends who you ask. Again, sometimes it's super difficult to defend Calcite because you want to do some pretty simple thing, and then in Calcite is very, very difficult. But at the same time, it gives you so many things. There were tons of times where we were saying, why this query is so fast? What is going on here? And suddenly we saw that we were applying some rule from Calcite that we didn't have to write, and it was already there. And it's doing, okay, cool, it's checking so many things, and suddenly, okay, cool, your query is super fast, and you didn't have to do anything. The case where we were talking about that before in ClickHouse, for example, there are tons of things we can do for free, super fast. So yeah, it's the interesting discussion.